I'm going to create a table that categorizes studies based on how the units were sampled from the target population and also how the treatment is assigned to units within the sample. So first we'll focus on how units are selected from the population. If those units are selected randomly from the population, then we expect that the sample will be representative of the population, and so we can generalize our results that we get from the sample to the entire population. So for example, if I'm interested in voters in Massachusetts, if I select a random sample of voters in Massachusetts, I should be able to use what I learned from the voters I've sampled in order to generalize to all of Massachusetts. If the units are sampled in some way that's not random, that doesn't mean that we necessarily can't generalize, but it's going to be a lot harder. We're going to have to demonstrate that the sample is representative of the target population on all the characteristics that we care about, and that is likely to be difficult. Then, if we have a sample and we're interested in comparing two treatments, we have to think about how those treatments are assigned. In other words, how do we decide which unit in the sample is assigned to one treatment versus another? So for example, if we have a sample of voters from Massachusetts and we're going to randomly assign them, or we're going to assign them to either have their doors knocked on or not, one way to do that would be randomly. If within our sample we randomly assign some of the units to be in one treatment and some to be in the other, then we can infer causation. In other words, if I randomly decide which units in the sample will have their doors knocked on versus not, then those two groups, knocked on doors versus doors that were ignored, should be comparable, representative of each other on all the possible background characteristics. And so I should be able to attribute any difference between them in terms of voting patterns on the fact that those doors were knocked on. So I can infer causation. I can learn about causation if treatment is assigned randomly. If treatment is assigned in some way that's not random, if I use some non-random way to decide which doors to knock on, it's going to be harder to infer causation. It's not impossible, but I'm going to have to demonstrate that the two groups I'm comparing, those whose doors were knocked on and those whose doors were not knocked on, are comparable on all possible background characteristics, and that is difficult. So if we use this table here to categorize studies, let's look at each of the quadrants. Ideally, we would first sample units randomly from the target population and then randomly assign the units in that sample to one treatment or another. That is almost never what happens in a study. It's too hard. It's too hard to do both. Rarely do you both have the capacity to choose your units in a random way and assign treatment in a random way. It does happen, but it's rare. It's fairly common to randomly select units from a population, but then compare groups of units within the sample that are not random. So the best example that I can think of is national surveys, polls of people from the entire United States. Often those polls are very well done in terms of random sampling, such that the people participating in the polls are representative of the target population. But then what people will do is take that data and say, okay, well, let's compare the people who were employed to the people who were not employed and see what we get. And in that case, we'll be able to generalize to the target population because we have a sample that's representative of the target population, but we won't be able to learn about, say, the causal effect of being employed versus not employed because we didn't randomly assign who was employed and who was not employed. So then we can think of studies where we did not randomly draw the units from the population, but we were able to randomly assign treatment. And one example of this is medical studies. So for medical studies, often the people who participate are volunteers, or they're recruited by their doctors. The people who participate in medical studies, including psychology studies, often are not representative of all possible patients. Rather, they're the people who are being treated at hospitals that are doing research. They're the people who are either so sick that they need to sign up for research in order to have any chance of obtaining treatment, or not that sick so that they don't care that much about which treatment they get. You're not going to get the people in the middle necessarily. Or the people who participate in research, in medical research, tend to be more educated than people who don't. So the units, the people who participate in the study are usually not representative of the population that we care about. But once those people sign up for the study, it's usually fairly straightforward to randomize who's assigned to one drug versus another. So in those cases, it's hard to generalize the results to the population of people that we really care about, all the people with a particular disease, but we can say something about whether the drug had a causal effect, whether it caused the people to do better for the type of person who did participate in the study. What about most studies? Well, most studies neither have random selection of units nor random assignment of treatment, which means it's hard to generalize the results to the target population, and it's hard to infer causation. There are things we can do to try to get closer, but our goal of both generalizing to the target population and saying something causal is often not able to be met. So does that mean we should give up? No. It just means that we need to be cautious as we interpret our results and make sure we're realistic in terms of what kinds of conclusions we're able to draw.